Hi everyone. Today we're going to learn about chemical equilibrium, specifically on the magnitude of K, the reaction manipulation, and the reaction quotient Q. So here's a page on the learning objective from College Board. You may want to pause the video for a moment and read it for yourself. The magnitude of K. K is a measure of how far a reaction goes. If the K equilibrium constant is greater than 10, the reaction goes nearly to completion. If K is greater than 1, equilibrium lies to the right. That means the forward reaction is favored and the products have higher concentration than the reactants. If K is less than 1, equilibrium lies to the left. The reverse reaction is favored and reactants have higher concentration. If K is equal to 1, system is at equilibrium, product concentration is equal to reactant concentration. Let's try practice problem number 1. Consider the reaction between carbon monoxide and 2 moles of hydrogen to make methanol. As equilibrium pressure, the mixture is in the flask of 5.19 liter, contains 0.270 mole of methanol, 0.961 moles of carbon monoxide, and 1.17 moles of hydrogen at a certain temperature. Calculate Kc, and does the equilibrium favor reactants or products? The first thing we do is to write the equilibrium constant expression, which is the concentration of methanol over concentration of carbon monoxide and over concentration of hydrogen raised to the power of 2. Then we plug in the numbers. Be sure you convert them into moles per liter. Now the Kc is calculated as 5.51. Because it's greater than 1, equilibrium lies to the right. Product is favored. Practice problem number 2. The diagram below shows a mixture of NO2 and N2O4 in a 1 liter flask at equilibrium at a particular temperature. What's the value of Kc? So let's take a look and count the number of molecules. We have 6 molecules of N2O4 and 7 molecules of the product NO2. Now we write the balanced equation NO2 converted into N2O4. And so we have 6 for the N2O4 and 7 for the NO2, but we have to raise it to the power of 2 because of the coefficient of 2. So now that's calculated as 0.122. Equilibrium constant is less than 1. Equilibrium lies to the left. Reverse reaction is favored. There are a set of rules when we manipulate the chemical equation, and that will change the value of equilibrium. The first rule is called the coefficient rule. If the coefficient in the equation are increased or decreased by a factor of n, then K is raised to that power. For example, N2O4 converted into NO2, equilibrium constant is 0.212. Now, if we double the moles from 2 moles of N2O4 to make 4 moles of NO2, the new equilibrium constant will be the square of 0.212, which is 0.0449. If we halve the moles, starting with half a mole of N2O4, and to arrive at 1 mole of NO2, the new equilibrium constant will be the square root of 0.212, which is 0.460. The second rule. The reciprocal rule. If the reaction is reversed, we will invert K. For example, the Kc is 0.212. Now we reverse the reaction into 2 moles of NO2 to make N2O4. Then we take the inverse of Kc, which is 1 over 0.212, which is 4.72. The third rule. Multiplication rule. If we add up the reactions, then the new equilibrium constant is the product of their individual equilibrium constants. Now, for example, in equation 1, 2 moles of SO2 to combine with 1 mole of oxygen to make 2 moles of SO3, K is 0.25. Now we take the sulfur trioxide combine it with water to form sulfuric acid, the K is 40. This is equation 2. Now find the Kp for our target equation, which is 2 moles of SO2 and oxygen and water to make 2 moles of sulfuric acid. Now let's take a look, compare the target equation to equation 1. The target equation has SO2 and O2 as reactant, and that seems to fit equation 1, so we'll leave equation 1 as if and don't change it. However, for the product, we need 2 moles of sulfuric acid. That comes from equation 2, but we do need to multiply everything by 2. Therefore, we will then square the equilibrium constant 40. So here is what I just said earlier. Multiply the coefficient in equation 2 by 2, and then take the square of the equilibrium constant. Then now you add up the equation 1 and 2 together, and then you get the target equation. And then we multiply the new equilibrium constants together, which is 0.25 times 1600, which is 400. Practice problem number 3. At 700 Kelvin, ammonia is decomposed to form nitrogen and hydrogen, and the equilibrium constant is 3.2 times 10 to the power 3. There's another equation. Ammonia then combines with hydrogen sulfide to form ammonium hydrogen sulfide, and equilibrium constant is 8.3 times 10 to the minus 3. This is equation 2. Now for the target equation, we have 2 moles of hydrogen sulfide with nitrogen and hydrogen to form 2 moles of ammonium hydrogen sulfide. Find the Kp. Now let's compare this target equation to equation 1, meaning that we need to flip equation 1 to reverse it, so we take 1 over the K value. And then for 2 moles of ammonium hydrogen sulfide, we need to multiply everything by 2 in equation 2. Therefore, we take the square of equilibrium constant 2. So now you add them, reverse the equation 1, take the inverse of K, which is 3.1 times 10 to the negative 4. You multiply equation 2 by 2, and take the square of the K, which is 8.3 times 10 to the power of negative 3, and square it. So now we add up the two equations, and we have the new K, which is the product of the two, which is 2.1 times 10 to the negative 8. Reaction quotient, represented by Q, it describes the relative quantities of reaction components at the initial state or at any state in the reaction. So mathematically, it takes the same form as equilibrium constant K. The expression is the same, except that it's based on initial concentration, and K relative to Q is a measure of the progress of the reaction toward equilibrium. So here's a diagram showing the how Q is relative to K. In the first diagram on top, you see Q is smaller than K. That means the equilibrium has not been reached yet. The product concentration is way too small, so the reaction will go forward to the right to produce more products to establish equilibrium, and the reactant concentration will decrease. In the second one, where you have Q is equal to K, the rate of forward and reverse reactions are the same. The reaction is at equilibrium. Now in the bottom diagram, where Q is greater than K, now the reaction has gone beyond equilibrium. That means the reactant concentration is way too small. Reaction needs to go back to the left to produce more reactants to reestablish equilibrium, and product concentration will decrease. Practice problem number 4. For the reaction A converted into B, the Kp is 5 at 290 K and 1 atmospheric pressure. In a mixture of A and B at that temperature and pressure, which one species is present in a greater amount? Now, because the Kp is equal to 5, which is greater than 1, that means the partial pressure of product B would be greater than the partial pressure of the reactant A, meaning product B is present in larger amount. If 2 moles of A and B were introduced into a container at 298 Kelvin, In which direction will the reaction go to establish equilibrium? The quotient is 2 over 2, which is 1, and quotient less than k, which is less than 5. So reaction goes to the right to reestablish equilibrium. To summarize what we have learned today, we learned how to use the magnitude of k to reason whether equilibrium lies toward reactant or product side. And secondly, the rule governing k when stoichiometric mole ratio or direction of the reaction are changed, or when reactions are added up. And finally, using Q versus K to predict and justify whether the reaction will go toward product or reactant as equilibrium is approached. From the team of MLCA, we'd like to thank you for watching the video and hope to see you again next time.